All right, again, good morning. So today we're gonna talk about big data, and the theme I want to approach here is it's constant evolution, and the fact that there's more questions and less answers in the big data world. So let's start with a question: who is this guy? Let me present you with a picture. So this is what I'm responsible for. It's the big data system within Akamai. It consists of about 150,000 collector nodes, and this is deployed at a planetary scale. So these nodes are all over the globe in about 1,000 or more different networks worldwide. We have about 5,000 MapReduce nodes, and we're processing billions, literally billions of data jobs, big data jobs every single day. So what is big data? For those of you that have seen or heard about big data, you've probably seen this picture, and they talk about the 3 V's or sometimes the 4 V's or the 5 V's. But generally you have volume is the first thing we think about in big data. Lots of volume. Anytime you have a lot of data volume, and we're terabytes or more, or if there's a big variety of data, structured or unstructured, and then if you have a high velocity or a need for high velocity on a large data set. So for some real quick examples here, in the volume case, we do some work in security around reputation scoring. So in order to develop a positive reputation score for an IP address or a user on the internet, we have to do a query over about 2 or 3 petabytes. So that's what we mean by volume. On the velocity side, we are processing about 50 million transactions every second. And although those transactions are not each very big, it's at a very high velocity. And a good example of variety of data is, for example, a Twitter feed. There's all kinds of unstructured data coming through. You have hashtags, text, and so forth. So that's an example of the kinds of variety of data. So some of the data that is big, and we'll focus on the upper boundary of this. You have mobile web data, messaging data, speech to text, video, audio, things like that represent big data based on its complexity and its variety. We have web logs on the other side, which when you get up to the planetary scale in volume, it's considered big data. So what is it really about? And that's a great question. I have no idea. I mean, we've been doing this for 15 years, and we're really just scratching the surface. And I think that's what's important, and that's why it's relevant to this conference, is the opportunities that big data presents to computer scientists and Java programmers are immense. We are really, literally just scratching the surface of what we can do with big data, in big data, and most importantly, what it's really about are the applications. Right? So we need to think about the tremendous possibilities with big data and what applications big data can drive. And that's where you folks come in. So to give you a little bit of history, when I say big data is all about the applications, we'll talk a little bit about the applications that drove big data to where we are today. And again, this is really just the tip of the iceberg. The world of big data is just starting. So for example, Akamai needed a billing system and a scalable monitoring system. That drove us, those are the applications that drove us to create a big data system. The open source community wanted a search engine. You may have heard of Nutch. That was one of the early drivers of big data in the open source community. Yahoo needed better product analytics. Google needed better computation or more scalable computation for ad placement. Facebook wanted real-time updates on their social graph. LinkedIn needed a real-time activity pipeline. Twitter wanted some hashtag and topic stream management. Amazon needed a durable shopping cart. And Netflix needed a recommendation engine. All of these applications drove the big data systems that we now know and use all the time. So a little bit of a timeline. You may not be able to read it, but what the relevant thing I think I want to point out here is that Akamai on the top of this timeline has been involved in big data from the beginning. So from 1998, we developed our first generalized MapReduce system. It ran on a single machine. Today, that same system is running on 5,000 machines with very little change in architecture. In 2001, we expanded our capabilities into from one machine to decentralized. We had a job scheduling, added more machines, and then you can see all the way through the timeline that we were developing new features, new capabilities, new products around big data that tracked quite well with the overall industry. And in the industry, we had things like Google File System, Google's MapReduce, which was actually 5 years later than Akamai's. We had Yahoo spun off Hadoop in 2006. Amazon created Dynamo for their shopping cart management in 2007. HBase was generated in 2008, Neo4j 2008. Facebook spun off Cassandra in 2008, and so on. So how does it work? So now we're going to get into a little bit of how big data works. And this is very much from an Akamai perspective because that's where our experience is. And feel free to interrupt me at any time with questions. So some of the big data modes that we'll operate on we have batch mode. So think about a database. You want to run a query or a transaction on a database. You have data statically in that database. You run your query. Same applies to big data. You'll run batch computations or MapReduce jobs or Spark programs on a relatively static data set. And the results that you get from that query or that job, that batch job, are generally complete. On the other hand, we have what's called online mode, and that is when we're doing the computation on the data as it's either being generated or being transported across the network. And these computations the results are localized. So you think about a distributed system where we have 5,000, or in our case, we have 150,000 nodes producing data. We are doing some processing at the producer. So on every one of those 150,000 nodes, we'll do a little bit of processing. It goes down to, it follows a tree or a graph hierarchy, and at each node, we do a little more processing. That's what we call online. And again, at any point in that tree or that hierarchy, you don't have a complete set of data. So you need to keep that in mind when doing these kinds of calculations and doing these kinds of jobs. And when I talk about calculations and jobs, they're really Java programs for the most part. In some cases, there are other languages being used, Lua and so forth. But generally, Java, and I think to emphasize that point that the big data ecosystem is driven by Java. And I think you guys are in a great position to really take advantage and advance big data in the industry. So some of the primitives, primitive operations that we perform in our big data systems are described here. We do collection, so data collection. We parse that data. We'll partition it. Partitioning is really an important primitive because when you get to huge volumes of data and when you want to do processing across a wide area, you have to partition it. And it poses some really interesting challenges. We do filtering, throttling, we aggregate, so combine like data. We need to track the data so we understand when it's complete. We do validation, and then finally, the whole purpose of all this is to provide some analysis or some application of that data. So let me get into collection. Any questions so far? Comments? There is a slide on throttling coming up, so absolutely we'll talk about that with some examples. So data collection is pretty straightforward. We just want to gather data into some kind of a system. So the types of data we gather are logs. So Akamai is a big collection of networks that's delivering products, and those products include content delivery, media delivery, security products, acceleration products. There's many products that run on the Akamai network, and they're all generating logs, and those logs are being collected and processed. We also have metadata, where our control data, so the control plane data that's used to manage all these products in these networks. We have system statistics, application events, application stats, and then networking data, router data, and interface data. So some of the ways that we actually collect this data include email. We use the Speedy protocol, HTTP post, scopy, scribe, avro, and then there's lots of custom collection mechanisms that we've developed. Parsing, generally you're reading a line or block of data, you split it into fields, and then populate a data structure, and then spin out some interesting data from that. So you think of, you'll parse a log and produce a bunch of tables. You may transform that into a protobuf format or some other wireline format. And then the map, and this is the map and MapReduce generally, will map keys to values. And with those key value pairs, we'll do our further processing. So here's an example of parsing. You'll see we have, in this case, it looks like a hit on a website, so like an Apache log or a Squid log. We'll parse that and produce, what we call pipelines, which are just different tables, different online tables of that data. And it's really just a matter of pulling out the fields and picking the fields you want for a particular pipeline. Partitioning, a couple of operations within the partitioning primitive will bucket the data. So generally you're producing, in our case we have about 50 million every second. We don't necessarily need to see every single event, every one of those 50 million every second. So we'll bucketize them. And for example, we'll put them into a 5-minute bucket. So we'll aggregate all those events into 5-minute buckets and sum up the values. Or we'll aggregate over a /24 address space. The other mechanism for partitioning is to hash. So we'll hash a record and direct it based on the results of that hashing function. We'll direct that data to one place or another in this graph, this overall worldwide graph. Filtering, here's where it gets really interesting and more on the computer science side, less on the system side. We often use statistical methods to filter our data, and we want to know things like what are the top K heavy hitters in a particular data set, or for example, what client IP is hitting this web server the most. That's an example of a top K type hit. And we'll use a data structure called a hierarchical count sketch to do top K calculations. We do Bloom filters for set membership, hyperlog log for cardinality counting, count sketches, frequency estimates, and then change detection. And this is extremely important when you're dealing with high volumes of online data. You really don't need to see every single event or every source record. You really just care about top K. And a good example of this is I was watching CNN this morning, and they were talking about some financial performance, and they said it was 50.3% improvement for the month. And when you think about that, is the 0.3 really important? Isn't 50% improvement enough? And that's kind of what we're talking about here, is we don't need to know that 0.3. The 50 is the relevant data. And these techniques help us to get that relevant data. We'll also do sampling, or sampling is very important in big data processing. And it's often just random. We randomly pick, say, one event out of a billion, and we'll send that along. And that gives us enough of a representation of the data set to make some intelligent decisions. Any questions on filtering? So throttling, throttling is mostly used for system protection. So in the case of like web-generated events, we can't necessarily control how many hits to the internet we're going to get. So we need to be able to throttle the data that's generated from those hits. So the way we do that is we'll limit the cardinality. So we'll limit the unique keys on a particular partition. So if you think of, in the case of web hits, we'll say any particular website can have 200 million unique keys per 5-minute period. The challenge here is that it requires some centralized management, because overall we're dealing with a distributed system. No one point in that system knows how many hits have happened on that website. So we need to centralize that, and that becomes very challenging and often brings us back to the statistical methods and filtering. When we do hit that system limit, we generally just drop the records over that limit for that time period. Another approach we'll use to throttling, and it's really more like thinning, is we'll drop some of the larger fields in a data set. So here's an example of that. Again, back to our web hit, we're dropping the URL and the cookie, for example, out of that web hit, and keeping the relevant points from the original data. Questions on throttling? Okay, another primitive within big data is aggregation. And this we do quite a bit because we're getting so much data. The volume, again, is, to put it in terms of sheer volume into our network, it's about 500 petabytes, 3 petabytes a day of data coming in that we need to process and aggregate to a point that it can be useful for someone doing analysis or generating invoices or reports. So the way we do aggregation is we need to sort the data. So we try and sort it online as close to where it's generated. And then we merge sort from then on. Once it's merge sorted, we can do a reduce operation. And this is the reduce in the map reduce primitive. And the reduce, in this case, we're looking at rows that have like keys. So 2 rows that have the same key, we'll just sum up the values for those 2 rows and make them into 1. And that's how we reduce the volume. And in Akamai, for our billing and reporting application, we get about a 30x reduction in volume using this technique. Another interesting aspect to aggregation is shuffling. Shuffling is about moving these blocks of data close to other data like it, or close to the consumer that's going to consume that particular data. And it sounds simple, but when you talk about large volumes over wide area distribution, it becomes very interesting. Tracking. Tracking is another complex operation that we need to do. And the goal is we want to understand at any point what's the completeness of our data. And this is relevant to financial data in particular. Anything that we're billing a customer on, we want to know how complete that data is before we send out those bills. So we don't want to send out a bill or an invoice if we only have 50% of our data collected. Nor do we want to send out an invoice if we have 150% of our data collected. So the techniques used for tracking is for every data unit that's sent or generated, we create a unique ID, and we embed that unique ID inside the data. We also publish that unique ID independent of data, and to measure the completeness, we'll gather all the unique IDs from the data set, compare it with the published unique IDs that were generated, and that'll give us a measure of completeness. Data integrity, we'll use watermarking. So the producer will put a watermark every n blocks or n lines, and that watermark is just a stamp that goes in a line on the data, and it's a crypto over the previous blocks or records. And then the receivers of the data checks those watermarks and fails blocks that don't have the correct watermark. We'll also use checksum, so you can do a checksum over a block of data or a CRC on every line or those kinds of things. On the analysis side, so once we do all these other primitives, we get the data to a point that someone can run an analysis. Some of the things that we do is we pre-compute reports. So we'll have streaming data that we incrementally generate a report that can then be queried much like a table in a database. On the batch side, we use Spark programs. These are essentially Java programs running on a Spark infrastructure. We'll do MapReduce programs, again, Java programs running on a Hadoop infrastructure. We do Hive, which is SQL-like interface on top of a Hadoop. And I'll talk about some of the applications, specific applications that use these primitives. Any questions so far? All right, excellent. So big data at Akamai. So Akamai has about 20 to 30 different big data systems for all of the various applications that require it. I'll highlight a few of them here to point out the vast differences in these applications. So our billing and reporting system, we talked a little bit about, but we have 150,000 producers that are generating data about the products that are running on the Akamai network. Those producers are generating logs that get sent to our processing system, which we call queue, parse, and pipelines. So we're receiving about 3 petabytes a day, and that doubles every year. What's interesting and somewhat evolutionary about this system is up to about 1 petabyte, we were receiving these logs via email. So all of these producers, these 150,000 producers, were emailing. Every hour, they would email us a log about the activity that they were generating. And we would receive that email on our queue interface, queue it up to be parsed, and then generate pipelines. Pipelines are essentially tables from those original logs. So again, we parse the logs into fields. We'll populate in this case, we populate about 50 different tables with various combinations of those fields. The parser also maps keys to values in those tables. Then we aggregate those pipelines to reduce the volume. So for an example, a pipeline would include a customer ID, the number of hits, and the number of bytes that were served on that customer. And that pipeline aggregates very well because across the entire network, it's the same customer ID, and the bytes and hits and bytes sum up nicely. Another example of a pipeline is our unique visitor pipeline. That has a key of client IP, user agent string, and often a cookie. And those don't aggregate very well, so they're extremely high volume. We then, once we have our pipelines, we start aggregating them. We'll then shuffle them either to a downstream consumer or split them to a reporting system or a billing database. So again, the evolution here is, as I mentioned, up to about 1 petabyte. We were emailing logs. We've since switched over to using the speedy protocol, and we're now in the process of moving over to HTTP2. So our system monitoring, this is an application called Query, and this is probably one of the most successful corporate applications in history of corporations. This has been so widely adopted and so well used over the 15 years since its inception. And what's brilliant about this system is it's completely, the use of it, the applications, the users are completely decoupled from the system itself. And the reason for that is we use SQL. So every single node and application across the network, and there are millions of them, they're all producing data into tables. And we can use SQL to query any one of those nodes or applications at any time. And the way it works is you have a client, you run a SQL statement, it goes out to this TLA, which stands for top-level aggregator. The top-level aggregator converts that SQL to a raw format, sends it out to regional aggregators, which then send it out to the source. The source then responds, brings the data back to the regional aggregators, and then follows this tree back to the top-level aggregator, and which sends the results back to the client. This is an extremely effective and efficient way to get data, monitoring data, out of a vast distributed network. This system is processing about 50 million jobs every day. Currently, our top-level aggregators are single machines, so all of your resulting data has to fit in the memory of a single machine. In the future, we're moving to more distributed memory. We have a media analytics system, and this is an example of using a columnar store for the data. In this case, the column store, or the DB, gets data from pipelines as well as events generated at the source, and it puts them all in a column store, indexes them, and then allows a reporting system to generate audience analytics, download analytics, and things like that. What's interesting about this application is that and you'll find this, that in big data, it's often about the trade-offs you have to make to solve your problem. In this case, and that means it's very slow to write to. We have to re-index the data every time we update our DB, but it's very fast to read from. And that trade-off was appropriate for this particular application. We've evolved this system. Again, this is all about the constant evolution of these applications and these systems. In this case, we're migrating the index, or from an index to a fingerprint approach, which is faster to generate. And we're also using a hyperlog data structure for uniqueness counting. We have security products. Security is a very fast-growing part of the Akamai product set, and it is an extremely complex big data problem. As you see here, we have data coming from many different sources, the Akamai edge networks. We have the Akamai web firewall are generating events. They're going into a database, a Hadoop HDFS system, running HBase as a column store and Hive as a SQL interface. We're using Cloudera and Graphite to manage this, and that enables our operations center to manage. This is about a 1,000 node cluster, processing about 20 terabytes a day, and it's managed by our 24/7 by our operations center. Some of the products that are generated off of this big data system include reputation scoring. So currently it's reputation. If you're a hacker out there or a botnet, we will track your activity and give you a reputation score so that a customer of ours or an internet provider can look at that reputation score and decide whether they want to deploy some kind of threat mitigation based on the reputation. We'll do threat analysis. We have intelligence reports, risk-based authentication, and some payment fraud systems. All applications on top of our secure big data. And again, the same theme here is it's constantly evolving. The applications are evolving, and we've just barely scratched the surface of what we can do with big data. One of probably the most interesting systems is our log archive. And what makes this interesting is it's extreme volume and it's distributed over a wide area. So what we're doing is we're archiving every single log, every event that's generated on the Akamai edge, and this is our 50 million hits per second. Every single one of those is being archived for 45 days. So that results in about 180 petabytes, or about 450 trillion records, which doesn't sound like much, but when you consider it's spread out over 90 regions over the wide area, it becomes really interesting to make queries against that size data. This data is also doubling every year, so we anticipate having 1.2 exabytes in about 3 years. The way this system works is you make a request to a front end. It checks, well, let me back up. The online processing to make this possible, we generate an index. So as the data comes in, we parse it and then index it. That index points our key fields, in this case, in a customer ID, an IP address, things like that. The index points those key fields back to what logs have data for those keys. The index itself is about 50 terabytes. So it needs its own big data system to manage. So we have a couple of different approaches to indexing. One is a straight flat file or MapReduce type index, and that will index your customer ID, the time frame, as well as the server ID, server IP that serve that content. We also have a client IP index. Now that indexes every single IP on the internet to what logs contained activity from that client IP. And that can't be done in any traditional DB or MapReduce approach, so we're using a sketch data structure, a probabilistic data structure to map client IPs to the logs that contain activity for that IP. So when you make a request, it checks using a Spark front end. It checks it checks your query in that index. Then it also checks the client IP sketch. Then it goes to a log cache, which contains about 10% of all data, gets what it can from there, then it gets the rest of the data from the 180 petabyte archive. And the challenges here, and the way this can be improved, is that the latency is really high. So you make a request, it could be hours before you get some data back. It could be 24 hours before you get your full set, or reach some 99 or 99+% completeness. And a lot of that has to do with the distribution, right? Again, this archive is contained in 90 regions distributed all over the world, over the wide area. So querying across that kind of planetary scale incurs latency. So we can solve that with smart partitioning, smart caching, try and cache the data that we think you'll need close to where you are. But again, we've just scratched the surface of the possibilities. And to talk a little bit about what's in this data, think about it, it's every single event on the internet. So Akamai is serving somewhere around 30% of all internet traffic. Every single one of those events is in this archive for 45 days. Think about the power of that and what you could do with that data set if you had access to it. We have no idea. I mean, we use it for some troubleshooting and product analysis and things like that. But the real opportunity here for you guys is in the applications that you can think of, you can envision, given fast, reliable access to a data set like this. So here's a kind of a snapshot of the current big data ecosystem, and this is taken mostly from the Apache Foundation. So it's around the Hadoop system, HDFS, Hadoop, Yarn. Yarn is just the next version of Hadoop. And you can see, the various capabilities, and I'll go through these in more detail specific to some various use cases. But we have HDFS is kind of the base layer. It's a highly distributed file system, or Hadoop file system. That's where the data, the blocks are stored. Hadoop is where you run computation on that data, and then the various ways that you can interface with Hadoop So if you want to write scripts, you use a module called Pig, and you write scripts in Pig Latin. If you want to do SQL, you use Hive. If you want to do NoSQL, which is like get and put, you use HBase. If you're dealing with streaming data or event-based data, you want to look at Kafka and Storm. If you want to search data, use Solr. And if you want to do in-memory processing, use Spark. And then there are some other tools for operating these big distributed networks. Any questions so far? So here I'll talk about a few examples of if you're building a system for a particular application. So in this case, if you need fast access to massive amounts of data where queries are constrained to an index, so you can do fast queries as long as they've been in data indexed. So you start with HDFS or Cassandra, you add an HBase column store, then you can add Hive for SQL access or Pig for scripting. And this is all software that's readily available on the Apache Foundation. You can install it on a single machine and get to work. It's all Java. Again, all of this infrastructure, this ecosystem is primarily written in Java. Another application you might have is you want to search logs for various services or products. In this case, you want to start with HDFS again, add Flume to do your data integration, and Avro to do serialization. So Flume, you can install Flume agents on your data producers. They'll send the data to Avro, which will serialize it, stream it over the wire to a collector that will deserialize it and publish it to HDFS. Once this data is in HDFS, it's available to Hadoop, MapReduce jobs, or in this case, Solr, which will allow you to do search, full text kind of searching. So if you need flexible and shared access to unlimited amounts of data, and what I mean by flexible, you don't want to be constrained by an index. You want to be able to run any query. You want to enable someone to run any query they could think of on this data set. So in this case, you again start with HDFS, add Hadoop, or Hive for SQL access, or Pig for scripting. So any one of these three will allow you to run any kind of query, regardless of how the data is stored or indexed. You can then add mesos to do resource sharing. This is important if you need multi-tenancy. You want to have multiple classes of users all sharing the same system. And then Ambari will do the cluster management, so it'll keep track of all the applications and nodes on your cluster. And then you can add your MapReduce, or your users can add their MapReduce programs for the business logic. So what's key here is that when this MapReduce programs, these are the applications. This is the rich capability that we have in front of us with this big data technology. This is where you can develop applications and data models that no one's thought of yet that add tremendous value to the community. So I think finally, if you need fast, flexible access to in-memory data, again, start with HDFS, Hadoop, add Spark SQL, or write Spark programs in Java to query that data. And what's unique about Spark is it pulls all this data into memory, allows you to do very rapid, low latency iterations on that data to produce results. Event processing, again, if you need an event processing system, an example of this would be like a pub-sub, publish-subscribe capability. You start with HDFS and then add Kafka and Storm, and then you write your online processing logic using what's called bolts, and those are also Java code. So some of the future projects at Akamai around big data include, we want to scale to 100x our current size, and that means everything has to get bigger and faster. So it's It's almost an overhaul of many of these components, lots of R&D being done across the many big data components we have. We also want to scale the big data ecosystem across the wide area. So currently, big data systems are deployed in big data centers, thousands of machines. I think Yahoo has a data center with 50,000 machines. And what we don't want is to have to build data centers that size. They're expensive, they use lots of power, and they're hard to move. We prefer to deploy in small regions, spread out over the wide area. So scaling the big data ecosystem, so Hadoop and that ecosystem across the wide area is extremely challenging. And we have lots of R&D happening in that area. Internet security, we're doing lots of work, lots of big data. Again, a lot of the security products are driven by big data. And some of the things we're working on are positive reputation scoring, which is a very difficult challenge because of the volume of data you have to look at. So for a really small example would have to query 3 petabytes of data. We're working on some automatic DDoS mitigation. So a lot of the attacks that we see on the internet today are denial of service or distributed denial of service attacks that Akamai can help to mitigate, but it often takes human intervention. So we want to automate as much of that as possible. Again, relies on big data and our ability to process big data with low latency. We are expanding our low latency data collection capability. In one example we recently looked at, we had 2 to the 53 unique keys, and we needed to collect that amount of data and make some sense out of it with very low latency, which poses some very interesting computer science as well as programming challenges. And then finally, we're moving into support of DevOps. So what this means is we need much closer to real-time monitoring and control systems. Again, given the size of our network and the volume of data, this is very much a big data problem that requires lots of R&D, science, and engineering and programming. So that's it. I appreciate your indulgence, and if you have any questions, feel free to ask them now or catch me anytime at the Akamai booth or around the conference. I'll be available and happy to answer any questions. Please come see us at Akamai, and we'll be happy to talk further.